Okay, so now I'm going to talk about inverting primes in symbolic geometry. First, I want to say about the classical analog in smooth topology. And let me just mention that this operation of inverting primes is also called localization. So I'm going to use that terminology. Okay, so what is this operation in classical topology? So this was something considered by Sullivan and Quillen in the setting of rational homotopy theory, and other people before them as well. And the operation is that you fix a set of primes P, and there turns out to be a functor from spaces to spaces, where spaces, I mean CW complexes up to homotopy that are simply connected, and it sends X to X at P. And the important property of this functor is that it localizes invariance. So the singular homology of X sub P is actually the localization of the singular homology of X away from the prime P, which basically you just tensor with Z with 1 over P inverted, so you invert P in singular homology. And also this construction of X sub P, it does depend on the CW presentation of X. You basically look at all the handles and the attaching spheres, and you replace those handles with what are called P handles. And then you prove that, in fact, the result only depends on the homotopy type of X. So if you have two presentations for the same space, then you do this construction of XP, a priori you get different things, but then you prove that, in fact, those things are homotopy equivalents. And for that, you need Whitehead's theorem. So that's an important ingredient. An ingredient that we don't have in symplectic topology. Let me say that. And third, this functor is idempotent. So if you apply it twice, it's the same thing as applying it once. So you should just think, okay, well, when I tensor with Z with 1 over P, if I do that twice, it's the same thing as doing it once. Okay. So that's the construction. And let me just give an example. The kind of canonical example is this infinite mapping telescope. So this is the P localization of a circle. You start with a circle, and then you take kind of infinitely many copies of it, and then you attach each one in the sequence to the next one by winding P times around. And you could check that the homology of the space is the localization of the homology of a circle. Okay, so it's some construction that looks like this. Okay. So this is the classical localization. It has these three properties. Now let me begin by talking about symplectic localization. Well, first, let me point out that the symplectic analog of a CW complex is a Weinstein domain, because a Weinstein domain comes with a handle body decomposition, just like a CW complex does.
Right. This something special will happen in degree 0, maybe. Like you say, the invariants localize, but I guess.
Oh, sorry. Oh, yeah, except degree. Yeah. Right, and I should also mention you could also do this construction when P is either 0 or 1. If it's 1, it doesn't do anything. If it's 0, it actually sends the space to a contractible space, and because inverting 0, making 0 an isomorphism just kills the whole group. So maybe I should say including. Okay. Yeah. Okay. So we want to find an analog of this in the symplectic setting. So we want some kind of operation that takes in a Weinstein domain and X and produces this PX, which satisfies these properties 1, 2, and 3, namely that invariants localize, it's homotopy invariant, and it's idempotent. So by property 1, invariance localizing, I mean that the Raphukaya category of this PX should be the localization of the Raphukaya category of X. So basically, I just mean you invert the prime P. And let me point out that we already have an example of this. And that example is flexibilization. And that's the P equals 0 case. Because in that case, the Raphukaya category of X flex is actually 0. I forgot if maybe I forgot to mention that, but it's true. The Raphukaya category flexible domain is 0, and you should think of that as inverting 0 in the Raphukaya category of X. But furthermore, so this just means it satisfies this first property, but furthermore, it's idempotent and well-defined by the H principle. So, right, because if you remember, these flexible domains are determined by their smooth topology. So if you start with one arbitrary Weinstein domain, if you flexibilize it twice, well, that's the same thing as that's flexible, and it has the same smooth topology as X. And you can also flexibilize once, and that also has the same smooth topology as X. And so by this H principle of Chilibug, Ashberg, and Murphy, those are two flexible domains with the same smooth topology, so they're the same. So that's this idempotence condition. And the well-definedness also actually requires the H principle, but it's true. I mean, the H principle says something stronger. It says that if you have two things which are only smoothly the same, then their flexibilizations are symplectomorphic. But what we're trying to do here is to slightly weaken that condition to conditions 1, 2, and 3, because there can only be one type of operation satisfying that if two things are smoothly the same, then they're symplectically the same, because that just says, in that case, you're just throwing away all of symplectic topology. But if you focus on these conditions 1, 2, 3, it turns out you can get more interesting operations. But anyway, so that's the goal, to come up with such a symplectic analog of classical localization, and we already have the case P equals 0, and I guess the case P equals 1, which you don't do anything. But what about the case of other P, which would give some kind of way of interpolating between not doing anything, which is, I guess, the rigid phenomenon, and flexibilizing at P equals 0? Well, there's results proven by Abu-Zaid and Seidel roughly 10 years ago, which says the following, which is that given a Weinstein domain X, where the dimension, this n, is at least 6, there exists some other Weinstein domain XP with a dash over it, which is diffeomorphic to X, and its symplectic cohomology is the localization of the symplectic homology of X. And the symplectic homology is some invariant you can extract from the Raphukaya category, but it is a weaker invariant. I mean, it's just some kind of algebra as opposed to Raphukaya category, which is a category. And let me say the idea of their construction. It's to start with some Lefschetz vibration for X, and to modify the vanishing cycles of that Lefschetz vibration. But you should just think of, you start with some Weinstein presentation, and then you modify the attaching spheres in some way. Now this operation, it does basically satisfy the first property of localizing some invariants, However, there are certain downsides. First of all, it's not really clear how X and XP prime are related, except via this construction where you kind of do these local modifications. So that seems very dependent on the presentation you pick of X, and there's not kind of a canonical geometric relationship between the two. So in particular, this property 2, that it's independent of the presentation, it's not clear at all if it holds for their construction. It's also not clear if it's idempotent. And because in the only case where we do know this is true, where the p equals 0 case, the proof uses the H principle. And in the smooth, in the classical setting, it uses Whitehead's theorem, which we definitely don't have in symplectic topology. So the question is, how do you, is there something like this in the symplectic setting where properties 2 and 3 hold? Are there questions so far? Okay. So let me first state a result joint with Zach Sylvan. So first of all, we kind of upgraded this result of Abu-Zaid and Seidel. We show that given a Weinstein domain X, where n is at least 5, there exists a Weinstein subdomain Px of X, which is diffeomorphic to X. So one with the property that its Raphkai category is the localization of the Raphkai category of X. So the main upgrade is that now this X sub P is not just kind of completely arbitrary, but it's actually sitting inside of X. So you get a kind of a singular Lagrangian in X corresponding to the skeleton of X sub P. And it has a different Fukui category from the Fukui category of X. And furthermore, it's a local modification of the attaching spheres. So there's some kind of local model, which I actually am not quite sure what it is. I have some ideas, but it generalizes these zigzags for these loose charts. So instead of putting in a zigzag, you put in some other model for the attaching spheres. And also, if p equals 0, you get a flexible structure. So we have some way of doing this coherently, and you get a flexible structure for x equals 0. So let me give a kind of application of this. So you could start with the standard cotangent bundle of a sphere. Now this theorem is going to produce inside subdomains for d primes. So you have the cotangent bundle, the 2 cotangent bundle, the 3 cotangent bundle, the 5 cotangent bundle, all of whose Fukui categories are localizations of the original one. So all these things have different Fukui categories. Basically, well, okay, that's some minor computation, but they all have different Fukui categories. But now, in addition, you can localize each of these, and so you get this kind of lattice. It turns out if you localize the 2 cotangent bundle kind of away from 3, or you localize the 3 cotangent bundle away from 2, you get the same thing, at least in this construction. I'm giving a particular construction so far. And you could do that for 3 and 5 to get this 3-5 cotangent bundle sitting inside of them. And you can keep going. You get this 2, 3, and 5 cotangent bundle. So you get this whole lattice, and it's an infinite lattice determined by collections of primes. And sitting inside the very bottom is the flexible cotangent bundle. Recall that the theorem I stated in the previous talk was had something like this, in a form like this, and this implied that this flexible cotangent bundle was sitting inside of the standard cotangent bundle. So here we have a generalization of that to arbitrary collections of primes, not just p equals 0.
Oleg, is it possible to get at least like a sketch of the picture what the local model would be in one of these examples?
So maybe, can you ask me that in like 20 minutes
Yes.
or 10
Okay.
minutes? Yeah. I'll say what the construction is, and the construction is pretty clear. In terms of the Lagrangians, it's not so clear in terms of the attaching spheres. That's kind of the difficulty, but I think it is computable. I have a guess of what it is. Okay, but in any case, you have this lattice of singular Lagrangians in a cotangent bundle sphere, and they all have different Foucault category. And I mean, this was. I don't know if this was expected. There is a conjecture, kind of a major conjecture in symplectic topology, that every smooth closed Lagrangian of a cotangent bundle is Hamiltonian isotopic to the zero section. And there's a lot of immersed Lagrangians and kind of non-exact Lagrangians, for which it's kind of harder to define Floer theoretic invariance. Here we have a different situation where the Lagrangians are themselves singular, if you want, they're subdomains, but the Raphoucaille categories are non-zero, and they do have interesting behavior. And so let me mention another result, which is that, so you have this lattice of subdomains where one sitting inside the other. In fact, the order of this lattice cannot be reversed. So for example, you cannot put the 2 cotangent bundle inside the 2-3 cotangent bundle. There's no symplectic embedding like this. Let me say roughly why this is. Well, if there were such an embedding, then you would have a Viterbo ring map going the other way, from the bigger domain to the smaller domain. There's also a functor on the Raphoucaille categories in the bigger domain to the smaller domains. Maybe that's better to say. But this symplectic homology of this 2-3 cotangent bundle is actually 0, because it's 2-3. You've inverted 1, you've inverted 3, but then when you look at it with Z-mod 3 coefficients, you get 0. Right, this 2-3 cotangent bundle is 3 inverted, so with Z-mod 3 coefficients, it's 0. Whereas the 2 cotangent bundle with Z-mod 3 coefficients, well, in Z-mod 3, 2 is already invertible. So in Z-mod 3. And so you're not really doing anything by inverting over Z-mod 3, so it's actually equal to the original cotangent bundle of a sphere. It's symplectic homology is equal to the symplectic homology of the original cotangent bundle, which is non-zero. And so you have a reunital ring map from a 0 ring to a non-zero ring, which is impossible. And there's also proof of this using the Foucault categories, but I think it's a little bit easier to state using these rings. Basically, you would have the Foucault category of the domain, bigger domain mapping to the bottom domain, and this is a localization, and it's impossible to have a localization functor from a 0 category to non-zero category. This is the algebra version of that. Okay, so you have this fairly rigid collection of Weinstein subdomains of cotangent bundles. In fact, of any domain, you have this lattice, but at least in the case of cotangent bundles, it's fairly rigid. And now let me state another result with Sylvan, which is that if you have M, which is the smooth manifold, which is simply connected in spin, then in fact any Weinstein subdomain X of the cotangent bundle of M has a Raphoucaille category isomorphic to the Raphoucaille category of the localization P for some set of primes P. So you have this fairly rigid lattice, and at least from the point of view of the Foucault category, any subdomain has the same Foucault category as one of those. So let me just say that this classification of subdomains is false in general. It definitely depends on the fact that we're talking about a cotangent bundle and subdomains of a cotangent bundle. It's false in general, namely, if you have some subdomain x naught inside of x, then it's not true in general that the Fukaya category of x naught is the localization of the Fukaya category of x for some prime p, even though this is true for cotangent bundles. And just a simple example is you could take a boundary connected sum of two cotangent bundles, m and n, and inside that you have a cotangent bundle of m, one of them. This is a subdomain, but it's definitely not a localization by some set of primes p, because you would have to kill the tn component without killing the tm component, and you can't do that just by localizing a subset of primes. So okay. Anyway, so far we have this operation of going from x to xp, which localizes the Fukaya category. It's a subdomain, so you get this lattice. In the case of a cotangent bundle, those are basically all the subdomains from the point of view of the Fukaya category. In general, it's just some lattice of subdomains, but there might be more stuff. Okay, so this basically addresses question 1, localizing invariance of the Fukaya category, but we still haven't said anything about the other two properties, this like independence of presentation and idempotence. So that's what I'm going to talk about next. So let me first mention two symplectically trivial operations which don't change the Fukaya category. So we've already seen one, which is subcritical handle attachment, where you attach a handle whose index is strictly less than the index, strictly less than half the dimension. This doesn't change the Fukaya category. Also, these subcritical handles satisfy an H principle by Gromov, so they're symplectically trivial in almost every possible way. There's also another operation which I haven't discussed yet, which is stabilization, which takes a domain to the domain cross T star D1. And this is no longer just a Weinstein domain, it's what's called the Weinstein sector. And it basically has two boundary components, using the fact that this T star Dn has kind of a boundary at infinity, and it has T star D1, it has a boundary corresponding to the boundary of D1. So you kind of leave the world of Weinstein domains, but this is this type of so there's actually a notion of the Fukaya category for these sectors. Sectors are basically Weinstein domains with some kind of extra sectorial boundary. And this operation also does not affect the Fukaya category. So okay, so we have these two operations which don't affect the Fukaya category and are somehow symplectically trivial. And so it makes sense to really consider Weinstein domains.
Oleg, can I ask a quick question?
These two. Yeah.
Yeah, so I mean, right, because before, right, like, so, yeah, right, you said that if I have a Weinstein manifold and I multiply by C, right, that form of stabilization kills everything, right? But basically this is the same, except that the Weinstein, well, it's not a Weinstein structure, it's like this sector thing now that still remembers stuff.
Exactly, yeah. So
yeah, can you say maybe, like why does this work better? Like why that?
Well, the Weinstein structure on this thing would be having a single critical point of index 0, or sorry, single critical point of index 1 at the origin, and then you basically require the Liouville vector field to be inward pointing near this sectorial boundary, or tangent. And so you have two critical points of index 0, which are still subcritical, but since they're pointing inwards, you also have this critical point of index 1. And so now it's no longer subcritical. Whereas in the case of C, you just have a single critical point of index 0, and when you take the product, everything becomes subcritical.
Okay, yeah, makes a lot of sense. Thanks.
Yeah. Yeah, but this is a key difference actually. But you could think of a sector as just a Weinstein domain plus a Weinstein hypersurface in the contact boundary. So that's another way of formulating that uses just domains plus the section data in the boundary. Okay, so these are these two operations, and now let me state this theorem with Sylvan and Tanaka, which is addressing these properties 2 and 3 that we want from localization. So the claim is that if x and x prime are symplectomorphic, then px and px prime are symplectomorphic up to stabilization and subcritical handles. So concretely, what I'm saying is if I take two different present Weinstein, so I have one Weinstein domain, maybe I apply some set of moves to it, I get a new Weinstein presentation. Then to each of those presentations, I do this local modification. A priori, I get different things, but in fact, I get the same thing up to stabilization and subcritical handles. So that's the claim. So this is addressing this independence of presentation, which we're claiming holds up to stabilization and subcriticals. We don't know whether it actually holds on the nose without stabilizing and adding subcriticals. I suspect that it doesn't, but it holds up to these moves. So this is some kind of, I would say, generalization of some weakening, but also generalization of this H principle for flexible domains. The other property is idempotence. So if you apply this p localization twice, you get the same thing as localizing once up to stabilization and subcritical handles again. The main point of all this, I think, is just that it's more natural to consider Weinstein domains up to stabilization and subcritical handles than Weinstein domains on the nose. Yeah.
And is there some hope that Thomas was asking, right, that maybe you want to do like simplification of intersections among Lagrangians if there's like the homological cancellation or whatever? Is it possible that by stabilizing, you gain this flexibility to allow you to really get closer to what the
yeah, I think, well, I don't know about homology. You still have the wrapped floor homology, which you have to deal with. But yeah, I think a lot of things will become more tractable. Let me just say, like, one thing I'm working on is to classify Lagrangians in like T star dn up to stabilization and basically up to stabilization. Whereas if you don't stabilize, there's actually like I have no idea what set of Lagrangians in T star dn is. But so yeah, stabilization definitely helps you first like do this operation, which is this theorem with Sylvan and Tanaka, but also I think it helps address other questions like classifying Lagrangians. I think that's true.
Okay.
Let me say one simple thing. So one thing that happens when you stabilize is that Lagrangians become disjoint. So you might have two Lagrangians in your domain. So okay, well let me just first say we also have a functor from some kind of category of Weinstein domains up to stabilization subcriticals, kind of analogous to the functor from spaces to spaces. But let me just say that suppose you have, addressing this question of Lagrangians, and why stabilization at least kind of helps. Suppose you have two Lagrangians, L and K, which might intersect in X, then what you're supposed to do is you're supposed to consider them as Lagrangians in the stabilization. You're supposed to cross it with a cotangent fiber at the origin. And in fact, these Lagrangians can be made disjoint. So, right, because this one is isotopic to, I don't know. to fiber at some other point. So this extra dimension allows you to disjoin them. Of course, this operation does not change the wrapped Fukai category, because when you do this wrapped Fukai category business, you have to wrap first, and when you wrap, the things do start to intersect, even though they seem disjoint. But this is definitely one benefit. And then, I mean, part of the proof actually uses things like this. Not quite this, but like one important fact is that you might have Lagrangian links, and everything becomes unlinked after stabilizing. That's actually something that does come up in the proof. But you have to do this in kind of a careful way, because you know the wrapped floor homology cannot change under this operation. So it's not like, you know, anything goes, but certain things now do become true. Okay, I hope that was helpful. Yeah. Okay, so now let me talk about the construction of this XP. Okay, so here's the idea. To construct at least a subdomain in general. So given a Lagrangian disk, D in X, the boundary of D maps to the boundary of X, then you can form a subdomain by carving out X. So kind of removing a neighbor, sorry, carving out D, removing a neighborhood of D. And the idea is that you should view an arbitrary Lagrangian disk as the co-core of some index and handle. And then this carving out operation is going to just remove that handle, and that's going to be the subdomain that you get. So to form subdomains, you want to look for Lagrangian disks. That's the point. And there's also a theorem of Ganatra, Pardon, and Shende, which is that the Raphoukai category of this carved out domain is isomorphic to the Fukai category of X, where you localize categorically by the object D. So basically you quotient out by the object D, you force it to be trivial, and if you do that, you actually compute the Fukai category of X complement D, this carved out domain. So, and this quotient, it only depends on D as an object of the Fukai category of X. Okay. Right, so I mean, maybe I should say an example. So suppose you have all of the co-cores, then you know when you quotient out by all the co-cores, they generate. And so this quotient is actually 0. On the other hand, the Fukai category of X complements all of these co-cores when you carve them out. Since you carve out all the co-cores, you're removing all the critical handles, and so this is the subcritical part, and this also has trivial about Fukai category. Okay, so that's the computation of the Fukai category of the subdomain. So now we just need a source of disks, and here I'm going to talk about some disks that were actually included, that were actually part of this paper of Abu Zaid and Seidel, although they used these disks in a different way, and it wasn't clear that they're getting subdomains. So let me back up. So suppose we have a smooth subdomain U inside of a sphere. This is just a statement of smooth topology. Then the claim is you could form a Lagrangian disk, so D sub U, inside the cotangent bundle of a disk with the following properties. So du will be isomorphic to some twisted complex of cotangent fibers at 0 in the Raphoukai category of T star dn, where the twisted complex is the one that uses the reduced I guess the reduced Morse cochain complex. So you start with this reduced Morse cochain complex of U. That's some chain complex, and then you tensor that with a cotangent fiber, and you view that as a twisted complex. the Raphkai category, and the claim is du is isomorphic to this. So constructing some du, and here's what object it is. And let me say a few words about what du actually is explicitly. So du is the graph of the differential of a function f from dn to r, and this function, it basically goes either to positive or negative infinity, and as you approach the boundary and of the disk. And remember, there's this domain U sitting inside of a sphere, which is the boundary of this dn. And as this function approaches, as you approach U, this function goes to negative infinity. As you approach other parts of the boundary of a disk, you approach positive infinity. So you have this function from dn to r, and then you take the graph of its differential, and that is a Lagrangian disk T star dn. Okay. So now the idea is to take U to be a P-Moore space. So a P-Moore space is just a space inside, so that its homology is reduced, homology is Z mod P. So it's reduced Morse chain complex has this form. This is what's called the cone of, this is the cone of P. So we take this special space, which is Moore space, and we use that space to construct this Lagrangian disk, which I'll denote dp. So U depends on P, and use that to construct dp. And now let me point out that you need an embedding of this Moore space into a sphere of dimension n-1. Or when I said embedding of Moore space, I mean it has to be an open, or sorry, it has to be a codimension 0 subdomain of the sphere, which is homotopy equivalent to a Moore space if you want. And this kind of embedding actually requires n to be 5 or greater. So if you recall, all of these localization results required high dimensionality, and in the construction where that comes up is this statement that like low dimensional Euclidean spaces or spheres do not have very complicated CW complexes sitting inside of them. Okay, so we got this Moore space, and we use that to form this disk by looking at the graph of a certain function. And so finally, what we do is, so remember, this disk is sitting inside T star dn, and each of the handles is basically a copy of T star dn, where the fiber corresponds to the co-core. So you have X with some fixed Weinstein structure, so it has some index n handles. Now, each of those handles is a copy of T star dn, and you embed this dp disk into the handle using this isomorphism between T star dn and the disk. So here I've drawn these dp disks inside X now. I've implanted them inside X, and now I carve them out. So I remove these disks. So here I guess I drew this in red to indicate that I was removing these disks. And okay, so now I have a domain with different topology because I've removed some handles. But now I can just like attach some handles along loose Legendrians to preserve the topology. So to summarize, I start with a presentation. Near each of the co-cores, I add these modified disks. I remove those modified disks, and then I reattach some flexible handles, which don't really do anything. Flexible handles, I mean, with attaching spheres that have these zigzags. Okay.
Maybe I misunderstood something, but before I thought that these spaces XP were actually subspaces of X.
Yeah, it is a subspace of X because I've removed, okay, yeah, I've removed a disk. So after removing a disk, it's definitely a subspace. But yeah, and then I'm saying I'm reattaching a flexible handle. That's true. But in fact, you can do that in a way so that it's still sitting inside of X.
As a symplectic manifold or as a
As a
smooth thing.
symplectic manifold, yes. So okay, this last step is only to preserve the topology. If you don't care about that, you don't have to do that. Sorry, the last step is only to preserve the smooth topology. Yeah, if you don't care about that, you could just carve out these disks and you're going to get these subdomains. But you can attach these flexible handles in a way so that the result's actually sitting inside of X still. Does that make sense? Okay. Okay. So now let's see what happens to the Rapid category. Well, by this, so the Rapid category of this XP is basically the Rapid category of X, where you move this DP disk. Okay, you attach some flexible handles, but they don't do anything to the Chi category. Then by this result of Ganatra, Pardon, and Shende, this is the same thing as this categorical quotient by this P disk. Now the P disks are all of the form this cone of P, this particular chain complex, tensor the cotangent fiber. That was a computation in observation societal. Now the fiber becomes the cocore. So this is what this DP disks looks like in the Chi category of X, where this is the cocore of X. And since the cocores generate, what you have is you're localizing, in fact, by the whole Fukai category of X tensor this complex. And the claim is that this is actually isomorphic to Fukai category of X with 1 over P inverted. Because when you're forcing this chain complex to be acyclic, that just means you're forcing P to be an isomorphism. Forcing P to be an isomorphism just means that you're inverting P. Are there any questions about this computation? So this proves that this XP has localized Fukai category.
Maybe, Oleg, can you explain again why the picture you made realizes this algebraically?
Well, the picture I made was this carving out. So I moved these disks,
Yeah.
and then moving this disk is the same as like killing this disk categorically.
No, but I should say so yeah. So why does again this DP correspond categorically to the object you write below? To this algebraic localization.
Are you asking about this?
I'm asking. No, I'm asking more like about the third isomorphism, I suppose. Like why DP, like why the picture you made for DP is exactly that cone.
Why it's that?
Yeah,
well,
I guess.
Well, with DP was, I mean, remember this DP disk? It was in a cotangent, a bundle of a disk, and there it was isomorphic to this cone of P tensor the cotangent fiber. But then when you embed the T star dn, there's a way of embedding T star dn into X so that the fiber goes to the cocore. And so this means that this DP, it goes to some other disk, which I guess I should really be calling DP bar or something, which is isomorphic to the cone of P times the cocore. because it's the cone in the cotangent bundle of Dn. It's the cone of a cotangent fiber. It's cone of P tensor the fiber.
Yeah, I mean, yeah. So that I understand. I mean, how like then this fits into the handle, I understand. But okay, maybe okay. Let's go on. Maybe, and I will bother you at the end to maybe
Okay.
like
Okay.
about the cone part. Yeah. Okay.
Yeah. I mean, the main point I would say is that killing this chain complex is the same thing as inverting P. And also, I guess I should say that this works for general. Oops. Okay. This works for general spaces U inside of a sphere. Here we just happen to pick a P Moore space so that we would have this localization. But if you pick just a general space, you're going to get some kind of how do I say? It's essentially a symplectic analog of what happens in say low momentum theory, where you localize by a space. So that's what's kind of going on here. Yeah, I mean, but of course, you would need more refined invariants like the Fukaya category enriched in spectra to distinguish like X sub U for different U. But I think that's something people are trying to do. But here we're doing the most kind of basic thing where considering the Fukaya category with integral coefficients. Okay. So that's the construction. Now let me talk about well-definedness, namely the statement that it's independent of the presentation and that it is idempotent. So okay, so this is a theorem joint with Sylvan and Tanaka, which is that if you start with X P and you stabilize that, that's actually the same thing as starting with X and then crossing it with the P localization of T star Dn. And also those two things are the same thing as X stabilized, and then you do this P localization. These are all three of these spaces are symplectomorphic up to subcritical handles. That's the claim. Where the space we are really interested is this space, but I've introduced these other two spaces. So this is the theorem I'll prove in a second. But why is this relevant? So X. So remember, we're changing the presentation of X, and the question is, if I take two different presentations of X, how am I going to ensure that the localizations are related by these Weinstein moves? Well, clearly, if you start with X and then you multiply with this localization of T star dp, dn, this is independent of the presentation of X, right? Like I'm saying, like if you have X and X prime are symplectomorphic, this implies that X cross this localized T star dn are also symplectomorphic. Just because taking products, symplectomorphism is preserved under taking products. So this second space is definitely independent of the presentation of X, because you're just taking a product with the fixed thing. And since all three of these are the same up to subcritical handles, this actually implies that XP is actually well-defined up to stabilization and subcritical handles. So it reduces to proving this statement. Are there any questions? Okay. Right. So and also you can prove idempotence in kind of a similar way. Let me just emphasize that as a consequence, you would be proving something like if you flexibilize twice, that's the same thing as flexibilizing once up to stabilization and subcriticals without using the H principle for loose isotropics with these zigzags. So this is going to give an alternative proof of a weaker result, but of course it applies in greater generality, where you're not just killing all the symplectic topology, you're only killing the symplectic topology like away from the prime P. Okay. So let me give a proof of this statement that these three spaces are the same. So, oh, and also let me just point out that when you stabilize this px, or you take the product of x with this p cotangent bundle of dn, these are actually not symplectomorphic. You actually need to add subcritical handles to make them the same in general. And that's just because if you look at the sectoral boundary of the first sector, it's xp cross t star sm minus 1, but the second one is x cross t star sm minus 1. So these sectoral boundaries are different. So these sectors are actually not symplectomorphic in general. Okay, so I just want to emphasize that subcritical handles actually are needed. So, but let's see, how are these the same up to subcritical handles? So let's just start with this this px and stabilized. Well, this is just x, where you move this this Lagrangian disk dp and you stabilize that. Now there's a Lagrangian cobordism, or sorry, there's a Weinstein cobordism to just the product, this x stabilized, and the critical points of this product correspond to pairs of critical points, and the cocores of the critical handles are the products of the cocores of the kind of the cobordism with the original thing. So the cobordism has cocore dp, and the only cocore of t star dn is this cotangent fiber. So I'm just saying this is some Weinstein cobordism. It has some subcritical handles. It has some critical handles. The cocores of the critical handles, well, there's only one, is something like this. Well, there's for any critical point of x, there's kind of a cocore that looks like this. So, okay. So let's see. So what does that mean? So that means there's a subcritical cobordism from xp stabilized to the product where I've carved out these critical cocores. Because again, the cobordism has subcritical parts and it has some critical handles. If I remove the cocores of those critical handles, I just have the subcritical part of the cobordism. And that's what I'm saying here. Okay. Well, I could also do this on the other domain I'm interested in, which is x cross t star d localized at p, this domain. So if I do that, I see that there's a subcritical cobordism to, again, the product where I've carved out a different Lagrangian disk, namely the cotangent fiber cross dp. Now, so I wrote these two disks here that I'm removing. Really, what I mean is that these are two disks in t star dn cross t star dn, but I'm identifying t star dn cross t star dn with a neighborhood with a handle, with a critical handle in this product, and the cocore, the original cocore, corresponds to the cotangent fiber, but I'm looking at these new disks and I'm modifying and I'm carving out these new disks. Okay, and now the point is that after stabilizing, and if you're an even dimension, then these two Lagrangian disks are actually isotopic in this T star dn cross T star dn. And you could check that because there's a map that swaps the variables, and you could show that it's isotopic to the identity. It's a very explicit ambient symplectic isotopy that swaps these two Lagrangians. But anyway, the point is that I have these two domains that I'm interested in, proving are the same up to subcritical handles. So I attach some subcritical handles, and I see that, well, I get the same domain up to carving out Lagrangians, which I claim are isotopic, and so those domains are symplectomorphic. So that's the main result. And oh, I guess I probably should have said this before. Yeah, how does this flexibilization come in? So this flexibilization is the p equals 0 case. So in that case, this Moore space, U should just be, I don't know, a disjoint union of two balls. I think that's right, inside a sphere, and from that you form this du, and this du, oh, oops, actually I think it should be 3. Or and this thing has this du is just the boundary connects sum of two cotangent fibers, which you're supposed to remove. To get the flexibilization. So this is x minus kind of the sum of the cocores. Anyway. Okay, are there any questions? I'm not sure how much time I have, if any. Maybe this is a good place to stop.